Hierarchical clustering is an alternative to k-means clustering that can be used when the number of observations is not too large. The main advantage is that you don't have to pre-specify how many clusters you have, but allow the data to tell you. First, we'll start with an overview of this approach, and in a minute, we'll look at a more detailed example. In stage 1 of hierarchical clustering, every observation is assigned to its own cluster. So if there are n data points, you start with n clusters. This is one reason why this is difficult to use with a large number of observations. In stage 2, join the two clusters closest to each other, that is, least dissimilar from each other. This results in n-1 clusters. In stage 3, again join the two clusters closest to each other. This results in n-2 clusters. And so on. Keep going until all the points are in the same cluster. This table shows an overview of this process. Starting at the bottom, in stage 1, there are n clusters, and as the stages increase, the number of clusters decreases until you get to the last stage, which has only one cluster. Here's an example to illustrate the process underlying this method. Let's say we're a B2B company with a catalog of products. We survey 8 customers and ask them 2 questions. Question 1, how many items would you like to see in our catalog? 1 equals very few and 7 equals many. Question 2, how much technical assistance and support would you expect from us? 1 equals none, 7 equals a lot. Here's a hypothetical plot of the responses to those 2 questions from our 8 customers. Each point represents one customer, and the location of that point shows their answers on the 7-point scales that we used. The x-axis shows the response on question 1 about the desired catalog size, and the y-axis shows the response on question 2 about the need for tech support. For example, customer 1 responded with a 1.5 on question 1 and a 7 on question 2. Each observation is assigned to its own cluster, so there are 8 clusters in this initial stage, stage 1. In stage 2, the closest 2 clusters are 1 and 2, so we join them. The others remain unchanged. In stage 3, the closest 2 clusters are 7 and 8, so we join them. The others remain unchanged, and we have 6 clusters now. We keep going, joining clusters closest to each other at each stage. In stage 4, we have 5 clusters. In stage 5, we have 4 clusters. Notice that within cluster variation is getting bigger as we include more dissimilar points. Stage 6, 3 clusters. Within cluster variation keeps getting bigger. This is the opposite of what we saw with k-means clustering, when we added one cluster at a time and the variation kept getting smaller. Here we are reducing the number of clusters, so the variation is getting bigger. Stage 7, 2 clusters. Notice that going from 3 to 2 clusters increases the variation by a large amount, so 3 might be the optimal number. But we don't have to eyeball it. We can plot the dissimilarity and see how it changes using a special chart called a dendrogram. This is a dendrogram. It's a type of chart that summarizes the clustering process and shows it visually. Admittedly, it looks a little weird. And yes, the name is definitely strange, but it does serve a useful purpose, as we'll see. The points or observations are shown on the x-axis, and dissimilarity is on the y-axis. As different observations get merged at each stage, the dendrogram shows, firstly, which observations are getting merged. So, for example, we see 1 and 2 get merged at the bottom left, and to their right, 4 and 5 getting merged. And secondly, it shows the dissimilarity of the points or clusters getting merged. This is shown by the height of the vertical line when they are merged. For example, when 4 and 5 are merged, the vertical line above them is a measure of their dissimilarity. Here's an interesting aspect of this chart. If you slice the dendrogram horizontally, the number of cuts, that is red X's, in the vertical lines tells you how many clusters have been formed at that point. For example, if you slice it just after the first 2 clusters are formed, you get 6 cuts, indicating 6 clusters. As you keep going up, you get 5 cuts, 4 cuts, 3 cuts, and so on. Remember that the vertical axis measures dissimilarity. You can see that the distance, that is, increase in dissimilarity from 4 to 3 clusters is not large, but the distance in going from 3 to 2 is much larger. So 3 is probably the optimal number of clusters. If you recall, this was the same intuition we had earlier when we were looking at the clustering process. But of course, at the end, we always have to ask, is the number of clusters managerially useful? Can management use this information to take some action? It's the same question we asked with k-means clustering as well. In conclusion, we need to consider what happens after you run a cluster analysis and you have formed the optimal number of clusters. What do you do with this information? Once you have identified the segments, examine their means on the variables you use to create the segments and plot them visually. Here we see that with our 3-cluster solution, Cluster 1 has a mean of 1.83 on the catalog size question and 6.33 on the technical assistance question. So they need a small catalog but a lot of support. We can call them the handheld segment. Cluster 2 has a mean of 6.5 on both questions, so they want a large catalog and a lot of support. Let's call them the demanding segment. Cluster 3 has a mean of 5.5 on the catalog question and a 1 for support. As long as they have a large catalog, they don't need much support and will shop on their own. They are the self-service segment. And that shows the purpose of segmentation. Rather than having 8 customers to deal with, we know we have 3 segments to deal with, and that's much more manageable. All customers in one segment can be treated as if they shared similar needs. Now that you've created segments based on customer needs, the final step is to create a profile of the segments. This allows you to learn more about who their members are and any information about them that might be relevant to your marketing efforts. For this reason, surveys often ask for additional information about respondents that is not related to their needs. For example, B2C companies typically want to know demographics such as age, gender, occupation, income, media habits, etc. For B2B companies, information about the industry that the buyer is in, their revenues, number of employees, is often relevant to their marketing efforts. All of this information is useful in developing a marketing and communication strategy for these segments.